All right, hi everyone. In this video, we're going to first work on this learning check. It was started in one section, but not the other. But we are asked to draw all possible configurations of 2-bromo-3-chlorobutane. And then for each configuration, assign each chiral atom as R or S. So the first step is just drawing out that molecule. You can ignore wedges and dashes initially. We just want to be able to identify where chiral atoms are. So I've got the molecule drawn, and I see that there are 2 chiral atoms. Each of those starred carbons are bonded to 4 different groups. Don't forget, each one has a hydrogen that is not drawn in. That is an implicit hydrogen. I will draw them in when we draw the configurations with wedges and dashes, although they are still not needed in those representations either. Okay, so that's the connectivity of the molecule. We've identified where chiral atoms are. Remember that each chiral atom can have an R or S configuration, and then we can have any combination of R and S for each chiral atom. So if I just start by drawing what I find to be the simplest representation, the simplest configuration, that is putting the substituents bromine and chlorine on wedges. And then I'll draw hydrogens in at this point. Okay, so that's configuration 1. I'll just put it as 1 here so we can count as we go along. Before we draw another one, let's go ahead and identify R or S for each chiral carbon. You might pause the video and try this on your own to make sure you can do it, and then you can listen to my explanation or just double check that you have the same answer. So for the chiral carbon on the left, the one bonded to bromine, bromine will be priority 1. Hydrogen will definitely be priority 4. And then we have the CH3 and, here we go, CH3, and then the CHCl, CH3. This will be priority 2 because it's bonded after the carbon bonded to a chlorine. And then this will be priority 3. Hydrogen is already in the back, so 1 to 2 to 3 looks clockwise, is clockwise. I'm going to erase just for clarity. This is R. Let's do the other chiral atom, so the one bonded to chlorine. That is bonded to, the chlorine will definitely be group 1, hydrogen 4, and then again we have this carbon bonded to bromine, hydrogen, and another carbon, and then this carbon which is just bonded to CH3s. So this will be priority 2, and this will be priority 3. Hydrogen's already in the back, 1 to 2 to 3 is clockwise, so this is also R. So in our first configuration, the combination of configurations is R and R. So if we draw the enantiomer of this molecule, we can do that by switching wedge and dash. So here on this carbon, we'll have hydrogen on the wedge, bromine on dash, and on this carbon, we'll have hydrogen on wedge and chlorine on the dash. This will be configuration 2. We've switched wedge and dash for both chiral centers. So these are enantiomers. Let's write this off to the side actually. So configuration 1 is RR. Configuration 2, since these are enantiomers, this one must be S and S. We've switched 2 atoms, or 2 groups, on each chiral carbon. So what was R became S for both chiral centers. That means that 1 and 2 are enantiomers. Now, another option is to switch only one of the chiral centers. So if we go back to the first configuration I labeled as configuration 1, where we have R and R, we could switch wedge and dash for just one of the chiral atoms. So I'll start with the one on the left. We'll put bromine on the wedge. Hydrogen on the wedge, bromine on the dash, but then keep the other chiral atom the same. So chlorine still on wedge, hydrogen on dash. This is just to draw another configuration, another possible configuration of this molecule. We've switched wedge and dash for atoms on the first chiral carbon. So that one will be S here. It looks just like this configuration. And then on the second chiral carbon, we kept groups in the same location, so that will be R. This is possible configuration 3. So I'm going to leave this over here. This is S and then R. Because only one configuration has changed, the configuration of one chiral atom has changed when you compare 3 to 1 or even 3 to 2. That makes the relationship diastereomers. So I'll write this over here. One and 3 are diastereomers of each other, and 2 and 3 are diastereomers of each other. Because if you just look at those pairings 1 versus 3, chiral atom or chirality of one atom changed, not both. And then if you compare 2 and 3, the chirality of one atom changed, not both. All right, let's do the last one, which is where the first chiral carbon keeps its original chirality from what we drew in configuration 1, but the second chiral carbon will change. So this is another possible combination. So I'm switching wedge and dash here. For second chiral carbon, that makes second chiral carbon S. Right here, this looks the same as the second chiral carbon in structure 2. First chiral carbon bonded to bromine is the same as the first chiral carbon in configuration 1. So this is 4. So again, adding to our list, 4 is R and then S. This means again that, let me see if I'll use orange now because we're going to have lots of lines here. So 1 and 4, only one chiral atom changed configuration. So these are diastereomers, 1 and 4. And then 2 and 4, same thing, only one chiral center changed chirality, so they are enantiomers. I'm sorry, they are diastereomers. If you look at 3 and 4, compare how chirality has changed. The first chiral atom bonded to bromine changed, if you start with 3 and then go to 4, was S, and then in 4 is R. Second chiral atom, the one bonded to chlorine, in 3 is R, in 4 is S. Between 3 and 4, each chiral atom has changed configuration, so these are also enantiomers. Now this is all the possible configurations. I'll write this a little bit more clear, what we have on the right side here. We could say diastereomeric pairs. and then enantiomeric pairs. I think enantiomers is easier. 1 and 2 are enantiomers, and then 3 and 4 are enantiomers. So 1 and 2 are mirror images of each other, 3 and 4 are mirror images of each other. For diastereomers, 1 and 3 are diastereomers, and then 1 and 4 are diastereomers as well. 2 and 3 are diastereomers, and then 2 and 4 are diastereomers. So we have 4 diastereomeric pairs, 2 enantiomeric pairs. And what I've just written at the bottom here is saying the same thing as what was drawn right there. Okay, so any molecule that has a chiral center, more than one chiral center, even if it is just one, it has 2 to the power of n possible configurations, where n is the number of stereocenters, or number of chiral atoms. And it's 2 to the n because for each chiral atom, there are 2 possibilities. It could be R or S. So for this example that we just went through, there were 2 chiral atoms. So we do 2 squared. This is 4 possible configurations, and that's what we drew. All right, we have a learning check here, which is we have 3 different molecules: acetaminophen, glucose, linear version of glucose, and pseudoephedrine. Acetaminophen is the active ingredient in like Tylenol, and pseudoephedrine is Sudafed, a decongestant. I'm going to save this for lecture when we're in person, but you can try this at home if you'd like. The question is just how many configurations are possible for each molecule. So we need to know how many stereocenters are there, and then use the formula that's on the previous page. I want to talk about optical rotation. This is an implication of chirality. So let's just start with this first part of the image here. If you start with a light bulb, like here, light bulbs have light emitting in all different directions. And so that's what these arrows are indicating, that light is coming out of that light bulb in a bunch of different directions. So that we call unpolarized light. If you send that light through a polarizer, then that polarizer, like this, it's almost like a shield. It will only allow light in a certain direction to pass through. In a real life example of a polarizer that you might have used before are polarized sunglasses. They actually have really small lines on them that prevent light from all different directions passing through. It polarizes that light so that it's only in one direction. Okay, so if you have polarized light, pass it through a chamber that doesn't have an optically active compound. We'll talk about what this means soon. If it doesn't have an optically active compound, then the plane of the polarized light, so the direction of that light, is unchanged by this compound. And then we'd say there's some analyzer at the end, and that would identify that the plane of that light has remained the same from the beginning to the end. If we look at the second image here, this is showing with an optically active compound. Optically active compounds rotate this plane of polarized light so that now, after that light passes through, it's not in the exact same plane. The plane has rotated a little bit. Then the analyzer would be able to determine how much that plane has rotated. So why are we talking about this? Well, molecules that have chiral centers are optically active. So if you shine polarized light through a sample of a molecule that has chirality, it will rotate the plane of polarized light. So chiral molecules rotate the plane of polarized light. We say that these molecules are optically active. If you have enantiomers, so mirror images, they rotate light to the same degree. So this degree here would be the same, but it would be in opposite directions. So if you have one enantiomer and pass it through this whole setup here, you'd have the light rotated in, let's say, just to the right a certain degree. Take the other enantiomer to put in this chamber, it would rotate light to the left, but to the same degree. This also means that if you have equal amounts of both enantiomers in the sample, this doesn't have to be a pure sample, if you have both enantiomers and equal amounts, it wouldn't rotate the light at all. They'd cancel each other out. So it says if a mixture contains equal amounts of both enantiomers, it would not rotate the plane of polarized light. This could be used, for example, to establish if a sample has enantiomeric purity. If you're looking for a sample that just has one enantiomer, or if it has an equal amount of both, then you'd be able to use how much that light rotates to determine if you have equal amounts, which means the light shouldn't rotate at all, or you have more of one enantiomer, that would rotate the light some. For our class, actually I should say first, there are a lot of different factors that determine whether a chiral molecule rotates light to the right or to the left, and the degree to which it rotates light. We're not going to go into that much detail in our class. For our class, I just want students to be able to determine if a molecule or a mixture is optically active or not. So if it is chiral, it is almost always optically active. When we come back, we'll learn about meso compounds, which are an exception. But for the most part, chiral, optically active. But if you have equal amounts of both enantiomers, we would say that that sample is inactive. It would not rotate the plane of polarized light. Okay, I'll end the video here. We'll do this last page in class, and then we will start Unit 4 notes. See you then.